All right, so let's start the second lesson as part of our fourth unit, or chapter 1 from our textbooks. And what we're going to be looking at is the sine, cosine, and tangent ratios from 0 to 360 degrees. So we're going to do a little investigation and discussion right now to kind of introduce what we're going to do. And this lesson is going to be broken down into two parts. They're going to be maybe two longer parts. I'll try to be as concise as I can be. But there's quite a lot to this lesson. So let's jump right in and get started. And so before beginning, I want to ask the question and make sure that we understand what does finding the sine of 30 degrees actually mean, or mean in words? All right, so I want us to think about that for a second. What does finding the sine of 30 degrees actually mean? Okay, and this deals with in a right angle triangle, of course. So if I were to draw a right angle triangle, and let's say this was a 30-degree angle, what does finding the sine of 30 actually mean? Well, in words, it means determining or finding the ratio of the opposite side to the hypotenuse. Okay, that's what it actually means. So it's finding, so if this is 30 degrees, this would be our opposite side. This would be our hypotenuse. And this, whatever ratio we find here, so it's going to end up being sine of 30 is equal to 0.5 or 1/2. Okay, and we know this from our last lesson in our special triangles, that opposite of 30 degrees, this is a special triangle, opposite of 30 degrees is our 1, and our hypotenuse is 2. And so when you do opposite to hypotenuse, you get 1 to 2, or 1 over 2, or 0.5. Okay, and this is true for any triangle, any right triangle with a 30-degree angle in it. So it doesn't matter that this is kind of our, think of it as our base triangle of 1 to 2, but let's just say we had a much bigger triangle. Okay, imagine we had a bigger triangle. Even if this measured to be, let's say, 5, all right, so let's say it was 5 times larger than that base triangle above, then this hypotenuse side would be 10. But we know that 5 over 10 simply reduces to 1 over 2 anyways. So for every single right triangle that has a 30-degree angle, the ratio of the opposite to the hypotenuse will always be 0.5, okay, no matter what. But that's only for right triangles. So that's where I wanted to start to help us understand a little bit deeper what these ratios even mean, okay? And my next question is this. So why are some ratios positive and negative? Okay, so I'm gonna attempt to kind of give the answer here. Maybe not the full description that we're looking for. That'll be part of our lesson. But let's dive into a little bit. Why are some ratios positive and negative? So for example, right? Let's take the sine ratio again. Let's stick with the sine ratio. If I do sine of 30 degrees, right, I get 1/2. We know that. Then if I do sine of, let's say, an angle 150 degrees, I actually get an equivalent ratio of 1/2. If you punch that into your calculator and you find the sine of 150, it equals 1/2. And then try punching into your calculator the sine of 210. And you get 1/2, but there's something that happens. Instead of positive 1/2, you end up getting negative 1/2, which sounds strange, right? Like, why on earth would we get negative 0.5 as our sine of 210? So you're probably wondering. And then also, if you were to take the sine of, let's say, 330 degrees, punch that into your calculator, you'd also get negative 1/2. So why? Why does this happen? Why do for these, now I obviously chose these angles specifically, 30, 150, 210, and 330, and I chose the sine ratio specifically of 1/2, okay? But why does this occur? And this is what the lesson today is all about, all right? It's about angles from 0 to 360, finding the trig ratios for any of the angles within 0 to 360. And so let's dive in and let's analyze why this could happen, okay? So let's just say I have a circle, okay, on a Cartesian plane. So a circle on a Cartesian plane. Now you might be wondering, why on a Cartesian plane? Okay, well, we're doing angles from 0 to 360. So from all the way around to here, I have 360 degrees going back, starting at my origin, going all the way around and ending again at my origin. Okay, that's 360 degrees. Now, let's say we were plotting our 30 degree. All right, now let's say we're plotting our 30 degree, and let's say that this circle has a radius of, I'm going to call it 2 units, and it doesn't matter what the units are, but let's say the circle has a radius of 2 units. And if I were to draw my radius line at 30 degrees, okay, so this is the radius of the circle, which is 2. Okay, sorry, my circle isn't by any stretch perfect, but that's the radius of my circle. And if I asked you, would you be able to find me the coordinates? So you know that this is 30. Would you be able to find me the coordinates x and y of the point on that circle? All right, and so again, where we're going with this is we're developing why sine 30 equals the same as sine 150, why it's the negative version for sine 210 and sine 330. So we're looking at developing that. I chose the number 2 on purpose and the angle 30 degree on purpose, okay, because it is one of our special triangles. So if I wanted to find the coordinate of this, okay, so all along here, this x value from here to here, seeing as this is a special triangle, this is actually root 3. And opposite of my 30 is 1. So what I did was, to find the coordinate, was I kind of dropped an imaginary line from my point on my circle. I dropped it straight down, so I made a 90-degree angle. And what I found was I have this special triangle. Okay, so if I wanted to write out the coordinate, then it's no longer just x and y. I can write it as root 3, square root of 3, comma 1. Okay, and that's because of the horizontal distance here and the vertical distance there. It's square root of 3, comma 1. So now when I find, this now makes sense why the sine of 30 equals 1/2. Because now when I do sine of 30 degrees, I know that it's opposite over hypotenuse, which this is, if this is my angle of reference, this is my opposite side, this is my hypotenuse. So you'd get 1/2. Okay. Now let's do the 150 and let's see why sine of 150 is the exact same as the sine of 30. Let's see. So if I were to draw a 150-degree angle, I'll approximate maybe to about here. That's about 150. And I still draw my radius of my circle, so I know that that is 2. By the way, the radius of the circle, I'll explain later. It always stays positive because it's a measurement. Okay, it's not a coordinate, it's a measurement. So it's 2 units always. So if it's 150 from here to here, by the way, 150 obviously falls short. All the way to this line on the x-axis would be 180. And so if it's 150 to this point, what is this remaining angle here? So if it's 180 to there, so this is 0, this is 90, 180, 270, and then 360 again. Okay? What is this angle here? It is a 30 degree again. Okay? And this is why the ratio ends up being the same. So it's 30 degrees again. and drop this line down, what's my coordinate now here? Well, I know that it's a 1, and I know that it's a square root 3 because I know it's my special triangle. However, it's not just square root 3 because now we're on the negative x-axis. It's actually negative square root 3. But for the y, we're still going up in the up direction, so we still have a positive 1 there. So the coordinate for that point would be negative square root 3, comma 1. And so once again, if we were to now do our sine of 150, it makes sense now that it equals 1 over 2. Because sine of 150 brings us to this point here. What's left over is 30 degrees with the x-axis. That's called, and you'll see later, that's called our related acute angle, 30 degrees. And so what we really just have, even though it says sine of 150, what we really are creating is a 30-degree triangle in the second quadrant with the x-axis. And so you still get opposite, which is positive 1, over the hypotenuse, which is always positive, but in this case it's positive 2. Okay, now let's look at if we were to do the sine of 210. So let's go all the way around now, and now we're down in this quadrant, we're passing 180, and we're down here, and let's say I'm going to draw my radius right there. Okay, I'm just going to make some room here and erase that. Okay, what is now, so if we went 210 degrees, so we went beyond 180 here, we went to 210. What is this angle here with the x-axis? If this is 210 there, and 180 was at the x-axis, what is this angle here, or the related acute angle it's called? If you guessed 30 again, it is 30, right? That's the relationship between all of these. They all create these 30-degree angle triangles. And then once again, if I were to create or find my x and y coordinates, I would have now the negative square root of 3 because I'm in the negative x-axis, but now I'm also in the negative y-axis. So it's no longer just 1, it's actually negative 1. The radius, because it's a measurement, it always remains positive. It's our hypotenuse in this case, but it always remains positive because it's a measurement, right? It's not a mathematical value on the Cartesian plane. It's strictly measuring what that line is, and it's 2 units. So now when you find the sine of 210 and you punch it into your calculator and you get negative 1/2, you realize that makes sense because now my opposite side is negative 1 divided by my hypotenuse, which is positive 2. Okay? And lastly, sine of 330 degrees works in the exact same way, right? I'm going to make some space. But if we were to have a 330 degree angle, means that we'd go all the way around to here at 330, okay? It's 360, so if this is at 330 and it gets 360 all the way to the x-axis, once again, that leaves us with a 30-degree angle as our related acute angle. And once again now, if I were to ask you the x and y coordinate, you would actually now get, because we're on the positive x-axis, you would get positive square root 3, but we're on the negative y right there, we're going downwards, so we're at negative 1. So the coordinate there is square root of 3 comma negative 1. Now when you do, now remember the hypotenuse or the radius is always 2, positive, all right? Now when you do your ratio of opposite over hypotenuse, you once again get negative 1 over 2. And so that is where your negative values come from. As you go beyond 90 degrees, you'll find that it's possible to get negative ratios. Everything in the first quadrant here, so if this is quadrant 1 in the top right corner, everything there will always be positive, whether you're taking sine, cos, or tangent of any angle, it'll always be positive. Everything's positive in there. The second you veer into the second, third, and fourth quadrant, you'll see that it's possible to begin to get negative ratios. And so this is the explanation as to why that occurs. Okay. With that, I think we're well equipped now. We have a little bit of background knowledge. I mean, I'm sure it's still very hazy to you, but obviously we're going to work on it. And we have enough background knowledge to actually get into our lesson. So let's go into our lesson here. Okay. And let's start with the basics. Let's start with some definitions. All right. So let's start with what's known as the initial arm. Okay, so the initial arm is always going to be on the positive side of the x-axis. So when you're given an angle, for example, right, and let's say the angle's 40 degrees, you're always going to start, this is your initial arm, you're always starting on the positive x-axis and then going 40 degrees. Okay? So you're going counterclockwise 40 degrees from the initial arm, which is on the positive x-axis. Then that 40-degree angle, that arm that now will go on the other side of that 40-degree angle, that's called your terminal arm. So that's called the arm created with an angle measurement. An angle measurement from the initial arm. Okay, so this is called your terminal arm. Now, standard position, all you need to know about that is the terminal arm always originates, okay, from the point 0, 0. So it always starts here, okay? That is what is known as standard position. The terminal arm will be drawn from the point 0, 0. Okay, so here's your initial arm. Okay, let's draw another example of that. So let's say that instead of having something in the first quadrant, we have something, let's say, in the third quadrant. So let's say we have 210 degrees, for example. You'd start on the initial arm on the positive x-axis, rotate around to 210 degrees, which would end up taking us to the third quadrant, right? If this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4, right? Going counterclockwise here. All right, so we're just going through some definitions, some names of what we're going to be drawing throughout this lesson, okay? A positive angle. So everything we've been doing so far has been positive angles, and they're all going counterclockwise, right? So they are measured from the positive x-axis and moves counterclockwise. Okay, so that's counterclockwise. And just short form CCW. But it's also possible to get negative angles, right? And so we're going to be thrown a few negative angles in this lesson here, in this unit. Don't be alarmed by it. All it means is that instead of going counterclockwise, you still start on the positive x-axis, but you rotate clockwise, okay? So it goes in the opposite direction. So measured from positive x-axis and moves this time clockwise, okay, not counterclockwise. So as an example, here is an example of a positive angle. So let's say something like this, starting from the positive x-axis or our initial arm. So let's say that this is something like 110 degrees. That's a positive angle. We're going counterclockwise. All right, so let's say that was positive 110 degrees. Now let's say we have negative 110 degrees. Well, we still start on the positive x-axis, but instead of going counterclockwise, we go clockwise. And we end up here. So let's say that was negative 110. Okay, so we just go in the opposite direction there. So don't be alarmed if you end up getting a negative angle. It just means that you have to go clockwise instead of counterclockwise. That's all. Okay, two very, very important definitions that you're going to hear me use throughout the next couple lessons, all right, is the idea of a principal angle and a related acute angle, okay? The principal angle is denoted by the symbol theta, okay, just a Greek letter in the Greek alphabet. And the related acute angle is always, or can be shown, I suppose, but mostly shown as beta. So the Greek letter, it looks like a B with like a line that goes further down. And this looks like a zero, kind of with like a continuing the zero and going through and drawing through the zero. Okay, that's how you would draw them. So when I say, or if I ask you to identify a principal angle, here's what I mean. It is measured from positive x-axis to the terminal arm. Okay, here's what I mean by that. So suppose I have a terminal arm down here. It is measured, the principal angle is measured from the positive x-axis to here. That is what's called theta. Okay, so we've already talked about some of those examples, right, but now I'm going to be referring to them from now on as the principal angle. Then you've got what's known as the related acute angle, and that is measured from terminal arm. By the way, this is our terminal arm. From the terminal arm to the x-axis, and it could be positive or negative x-axis. Positive or negative x-axis. So it doesn't matter whether because the principal angle has to start on the positive x-axis, okay? Whereas the related acute angle is just measured from the terminal arm. So let's say from here to any side of the x-axis, whether it be positive or negative. So this is what's known as our beta. Okay, so in this case, it's from the negative x-axis to the terminal arm. Suppose we are in this quadrant. Okay, the principal angle would be starting from the positive x-axis and all the way around counterclockwise. If it's a positive angle, it goes counterclockwise. If it's a negative angle, it goes clockwise. So this is theta, which leaves this angle right there as our beta. So it's from the terminal arm to any side of the x-axis. Okay. Now, I guess I should also explain, because you're probably wondering, well, what about in this first quadrant here? What's the deal with beta and theta, or the principal angle and the related acute angle? So let me draw another example. If your principal angle is in the first quadrant, so let's say right there, okay, let's call this theta. So it's starting from the positive x-axis up to touching the terminal arm. You might have noticed that theta actually equals beta in this quadrant, right? Because in both cases, they end up being the same value, right? Theta starts from the positive x-axis to the terminal arm. Well, it's in the first quadrant there. And beta goes from either side of the x-axis. In this case, obviously, it'd be the positive side to the terminal arm as well. Okay, so they end up being the exact same there. It's the only quadrant where theta and beta end up equaling each other. Okay, so make note of that. Continuing on. Okay, let's get to just let's get our feet wet just with some simple set of examples here. So sketch each angle in standard position. Okay, state the principal and related acute angle. No problem. Okay, so let's start with the principal angle of 240. So this is going to be our theta. All right, that's what they've given to us is theta. So we're going to go 240. Now remember, this is 0, 90, 180, 270, and then back to 360, right? 240 is going to be somewhere in that quadrant. So we're going to go around 0, 90, past 180. Before we get to 270, we'll stop, draw our terminal arm, call this angle 240. So theta equals 240. Beta then, how do we figure out beta? Let's do a calculation. How can we figure out the angle from, this is beta right there. So from the negative x-axis to the terminal arm. How can we figure out that calculation? Well, if it was 240 all the way around, and we want to go back measuring this way, the difference between this point and this point right there, if we subtract it from 180, we should get what's left over inside that related acute angle, and it's 60 degrees. So I did 240, my theta, and I subtracted, just looking at my Cartesian plane, I knew that I needed to subtract 180 there. It's not always going to be like that depending on what quadrant you're in, and you'll see with our other examples. Okay, beta, you're going to have to be flexible in trying to calculate what beta is in each quadrant. Okay, so now we have negative 75 degrees. Next example. Okay, negative 75 takes us clockwise somewhere down here. Okay, pretty sloppy there. Sorry about that. That's negative 75. Well, right away I can look at that and say, okay, my beta then is going to be 75 degrees, right? Because from my terminal arm to my positive x-axis here, I'm clearly going to be 75 degrees. That's going to be my related acute angle. Okay, and you don't say it as a negative 75. You say it as a positive 75 degrees. Related acute angles are always, always, always positive. Okay. Theta is going to be a little bit harder to calculate in this case. My principal angle starting from this side going all the way around to here is now my principal angle theta. So from the positive x-axis to the terminal arm going counterclockwise. So how do we figure out theta in this case? Well, if it's 360 all the way around and then we go back 75 degrees, right? Like if we were to go all the way around to 360 and then go back 75, well, then our calculation there to figure that out would be 360 minus 75. Okay, so it'd be 285 degrees. So it's going to be different each time depending on the quadrant you're in. Like let's look at the next example. 138. So we're starting on the positive x-axis, going clockwise to 138, somewhere there, right? If this is 0, 90, 180, 270, and then 360. We're going to be in the second quadrant there. So theta, very simply, will simply be our 138 degrees. It's our principal angle going from our positive x-axis to the terminal arm. Our beta, however, requires a little calculation. How are we going to figure out that angle in there? Well, again, if it's 180 all the way around, okay, and it's 138 up to here, what's left over? Well, if we take 180 and we subtract 138, okay, you get 42 degrees. So our theta is 138, our beta is 42. Okay? It'd be a good idea now to pause the video, go into the homework questions that I've assigned from my website, and practice these specific types of questions, finding theta and beta. Okay? All right. Hopefully you've done that. And let's move on, okay, to something that we've kind of already somewhat determined when we did our discussion at the start of this lesson. But let's go ahead now and do maybe a more descriptive solution, okay? So let's find, using our calculator, first off it says sketch each angle, no problem. 50 degrees is here, right there. And it says to use our calculator to determine the trig ratio. So let's find sine 50. Let's do this to 4 decimal places. It's 0.7660. And again, remember what that means, that the ratio of the opposite side here to the hypotenuse is 0.7660. Okay? Sine of 150, we already did this, it's 0.5. Sine of 250 ends up being negative 0.9397. Okay? Sine of 350, negative 0.1736. And again, let's draw it in the specific quadrant. So sine of 150 is about there, right? 250 goes all the way around but doesn't pass 270, gets close to it. This would be our 250. And 350 goes almost all the way around but stops before 360, or let's say right there. Okay, there's our 360, or 350, sorry. All right. Now watch this. If sine of 50 is 0.7660, let's find out what the cos of 50 is. So the ratio of the adjacent side to the hypotenuse is 0.6428. Something to note is that it is a positive ratio there. Tan of 50, the ratio of the opposite to the adjacent side, is 1918. Okay, 1.1918. And again, it is also positive. You'll find that when you punch those into your calculator, you get a positive value. And it has something to do with the quadrant that it's in. That's the reason why they are all positive. But if you remember from the discussion, I told you that there's some ratios that end up being negative. So let's find the cos of 150. And when you find that in your calculator, you actually get a negative ratio. Negative 0.8660. It makes sense because if the ratio of the adjacent to the hypotenuse, okay, so let's call this 30 degrees again, we know that this would end up being, and the coordinate here would end up being negative square root 3. So the adjacent would end up being negative because it's on the negative x-axis, divided by the hypotenuse, which is positive. And that's where you get the negative 0.8660, because it's a negative divided by a positive. Tan of 150, you'll find, is also negative. So the opposite divided by the adjacent will also be, well, the opposite is 1, divided by the adjacent, which is negative square root 3. Of course, you're going to get a negative ratio there. Let's look in the third quadrant. Sine of 250 ends up being negative. Cos of 250 also ends up being a negative ratio. However, the tan of 250 ends up being a positive ratio. Okay? So let's make note of that in this quadrant, everything was negative except for the tan ratio. And in this quadrant, everything was negative except for the sine ratio. And then, of course, in this quadrant, all three were negative, or all three were positive. Let's look in the final quadrant here, our fourth quadrant. Our sine ratio ends up being negative. Our cos ratio this time ends up being positive, while our tan ends up being negative. It makes sense that cos is positive because we're on the positive x-axis right there. And because it's adjacent over hypotenuse, okay, adjacent over hypotenuse, the adjacent side is positive, and remember that the hypotenuse is also always positive because it's the radius of the unit circle, which is a measurement. And in measurement, we always give positive values, the absolute values, okay? And so in this quadrant, we found that cos was positive. Here, tan was positive. Here, sine was positive. And everything else was negative. And here, all positive. Right? Okay, and so now we can come up with what's known as the cast rule. All right, so if I have the cast rule and I write each, it's basically just an abbreviation, something to help you remember in which quadrants is which ratio is positive. So we said that here, all ratios positive. Right? Whereas here we said that the sine ratio is positive. Here we said that the tan ratio is positive, and here we said that the cos ratio is positive. All right, and so that if we're in this quadrant and I know I have to take a cosine ratio, I know that I'm going to end up getting a negative ratio. If I take the tan ratio, I know it's going to end up being negative. The only ratio that will be positive in that quadrant is if I take the sine of an angle that's in that quadrant. Okay, so let's summarize now. Let's summarize how to determine an exact value of a trig function. Okay. Okay, so before I summarize the steps, let's start an example, and then as we work through the example, we'll write out what the steps are, okay, for this first example. So the question is, determine the exact value of each trig ratio. So we have cos of 315, which means that our principal angle is 315 degrees, and I have to find, without using my calculator, and it says the exact value, meaning no decimals. If you see the words exact value in this unit, we are going to be using our special triangles somewhere. You know that because only our special triangles will help us or provide us with exact fractions or exact ratios and no decimals. Okay? So we know that there must be a special triangle somewhere here. Well, let's see what they're talking about. All right, so we're going to draw a principal angle. Let's draw this out. I think step one, of course, should be to draw a sketch, right? So we're at 315. So we're going to be in this quadrant, in the fourth quadrant here. By the way, using the cast rule, which ratio should be positive in the fourth quadrant? Cosine. All right, so we expect to get a positive ratio here. Let's see what happens. So let's go 315. So we're going to go, let's draw it somewhere, I don't know, let's say there. Okay. So let's call that 315, which is our principal angle. Well, in order to figure out our exact values, we have to make some sort of relation to a special triangle. So if I were to draw a right angle triangle here, and I were to find my beta, this is beta, my related acute angle, Maybe it'll be a special triangle. Maybe it'll be an angle that exists in a special triangle. Okay, so let's find beta as kind of my step 2. Beta is equal to, how are you going to find the related acute angle? Well, if we go all the way around to 360, right, and if we subtract 315, we should get what's left over in that related acute angle. And look at that. We do end up getting a special triangle of 45 degrees. So let's label my special triangle now, since my related acute angle is 45 degrees. Okay, so let's label it. I've got a positive 1 here because I'm on the positive x side. I've got a negative 1 here because I'm on the negative y side. And remember, the radius or the hypotenuse is always positive. Always positive. It's a measurement. It's the square root of 2. So we found the related acute angle, and that helped us realize that we had a special triangle situation where I can find the exact value. So now when I find the cos of 315 degrees, right, I know that it's equal to the adjacent divided by the hypotenuse, which in my case, the adjacent is here, the hypotenuse is here. It's 1 over square root 2. And do a check for me. In your calculator, type in cos 315, all right? Remember that number. Now type in 1 divided by the square root of 2. You should get the exact same answer as the cos of 315. And so what we did, instead of just plugging it into our calculator, we found an exact value of 1 divided by the square root of 2, as opposed to providing a decimal. Okay, so we have satisfied and answered this question. Now let's summarize the steps we took. We started by drawing a sketch. So draw a sketch where the terminal arm will lie. So which quadrant, right? We need to know what quadrant we're working in. Secondly, what we did was from the quadrant we were in, we were able to determine beta, right? We were able to determine the related acute angle. So next is determine the related acute angle, beta. Okay, so you drew a sketch of where the terminal arm is, in which quadrant. From there, we figured out beta. Okay, from there, we label the triangle. Now, this is specifically to using exact values. This is specific to special triangles, okay? So we labeled the triangle according, but not all questions are going to be like this. They won't all be use the exact value, use the special triangle, okay? So this is just specifically for exact triangles. Label the triangle according to special triangles. Okay? And then lastly, we determine the ratio. And notice we got a positive ratio of 1 divided by square root 2. It's positive, it's not negative. We expected that because it's in the 4th quadrant. We know that the cosine ratio will be positive in that quadrant. So determine the ratio based on special angle and trig ratio given. So in our case, the given trig ratio was the cosine, right? It said find the cos of 315. Okay, so in our case, it was cosine. I'll do one more example with you. Let's do the tan of 120, okay? So Step 1, draw a sketch of where 120 will be. It will be in the second quadrant here, right? If this is 90, 180, 270, 360, and 0, right? So it'll be somewhere here. This is our theta is 120. This will be our beta. We have to, step 2 says, find what beta will be. Well, to find beta in this particular quadrant, if we take all the way around 180 and we subtract 120, we get what's left over for beta, and that's 60 degrees. Well, guess what? 60 degrees is another special triangle. So let's draw our triangle. Okay. If the beta 60, opposite from there would be our square root 3. 2 would be our hypotenuse, and 1 would be our adjacent side there. However, because we're on the negative x-axis, it would be -1. Okay, but our square root 3 is positive because we're going upwards in the positive y direction. So it's just positive square root 3. Now, let's take the tan. Let's do tan of 120 is equal to opposite over adjacent, which is equal to square root 3 over -1, which is equal to the negative square root of 3. Try it on your calculator. Take the tan of 120, make sure you're in degree mode, hit equals, and then try doing -1 times the square root of 3, and you should get the exact same answer. And we expect tan to be negative in this quadrant because if we do the cast rule, the only ratio which will be positive is sine in quadrant 2. Tan and cosine will end up being negative. Okay, so there's our final answer, negative square root of 3. I know this is a long lesson, okay? We have one more set of examples. I'll do 2 more. We'll make a summary of the steps as well. And then this is only part 1 of our lesson. This is a long lesson. There's a lot to take in here. Part 2, I'll make in a separate video. All right, so next it says, state an equivalent expression for each trig ratio. Ooh, okay. An equivalent expression. So finding the sine of 290, if we were to punch that into our calculator, what do you end up getting if you were to punch sine of 290 into your calculator? Okay, so you'd end up getting a negative ratio, which makes sense because you'd be in the 4th quadrant, and it's a sine ratio, so only cosine is positive in the 4th quadrant. But it'd be negative 0.9, let's just round it right now to negative 0.94. So we have a negative ratio, okay, negative ratio. When it asks for an equivalent expression, it's asking for, in this case, where else will sine be negative? Because we got a negative ratio, right? So we're down here. We're down here. We're 290. We're down here, right? We know that we have a negative sine ratio here. Well, we want to find an equivalent expression, so we also want to find another place where we'll get the same value and also be negative. Okay? Here's what you do to do that. First, ask yourself, where else will sine be negative here if we follow the cast rule? It'll be in this quadrant, right? Because it'll be positive here and it'll be positive here. It'll only be negative in the 3rd quadrant here. So our terminal arm needs to be somewhere here in the 3rd quadrant in order for them to be an equivalent expression. And watch this. If we find beta, okay, what does beta equal here? 360 minus 290. Okay, which is 70 degrees. If we take that related acute angle and we apply it here as well, and we do a 70-degree angle there, okay, we can now figure out theta, or our principal angle, from here to here. And that should be an equivalent expression. So to recap, I drew my terminal arm. First, I figured out, okay, what do I have, a positive or negative ratio here? I had a negative ratio. So I figured out where else is sine negative. It's in quadrant 3. Then I calculated the related acute angle and drew it in quadrant 3. And now I figure out the principal angle for that arm. So theta equals, we got to go 180 plus another 70. 250. So watch what this means now, is that sine of 250 should equal sine of 290. Test that out on your calculator right now. See if we did everything right here. Okay, sine of 250, if you were to take the sine of 250, you end up getting negative 0.94 as well. So our equivalent expression is sine of 250. It's exact same value as sine of 290. They're both negative and they both are the same magnitude as well. Okay, now if we were to summarize our steps there, because I think we really need to do that, this gets a little confusing. We need to draw a diagram, draw a sketch of the terminal arm. Okay. From there, we had to figure out the related acute angle. So determine, so the first two steps are just like above. Determine related acute angle, beta. From there, we asked ourselves, okay, do we have a positive or negative ratio based on where our terminal arm is? So we just punched it into our calculator, like we punched sine of 290 right into our calculator, just to help us determine if we have a positive or negative ratio. So determine whether there is a negative or positive ratio given. Based on that, whether it's negative or positive now, you have to determine the quadrant, that provides the same sign, so positive or negative. Okay, so we determine the quadrant that provides the same sign and solve for theta, or the new principal angle. Okay. Let's try one more question. We'll do question C here just to give us more space. So find the tan of 135. All right, so grab your calculator, find the tan of, that's step 1. We have to figure out, oh, step 1, I guess, is draw a sketch. Sorry, let's draw a sketch. 135, we're in this quadrant here. Okay. Find tan of 135. Let's find out. Do you get a positive or negative ratio? Well, I know that just from the CAST rule, it's going to be a negative ratio because it's tan in this quadrant. Only sine is positive in that quadrant. So I already know it's going to be negatives, but let's double check. So I'll do tan of 135, and you get negative 1. Okay, so now we ask ourselves, where else is tan ratio negative? And it's here in quadrant 4. So I'm going to write the terminal arm in this quadrant. Okay, that's where we're going to find an equivalent negative expression. Next is I'm going to find beta. And I'm going to apply that same beta right there. Beta is equal to 180 minus 135, which is 45 degrees. Now, to find my equivalent expression, if I know this is 45, I just need to find the principal angle that goes to this new terminal arm, which is going to be, go all the way around to 360, subtract or go back 45 degrees, okay, which is 315. What this now means is that the tan of 135 should equal the tan of 315. Double check them, and they do. Okay, so we just came up with an equivalent expression. Tan of 315 is the same as tan of 135. The exact same sign and the exact same magnitude. So there's a lot to take in from this lesson. All right, this is probably the longest and probably most challenging lesson of the course, perhaps. It's important to get this down right. If you take advanced functions, this is imperative that you understand this. Also, in college, you certainly, if you're taking any sort of more advanced math, you'll have to have this knowledge, or you'll go back over this stuff and you'll just have such an advantage if you understand this. Okay?